Good morning and welcome back. Today I'm going to discuss fundamental concepts regarding Quaternion. And as I told you earlier, Quaternion is an alternative tool for representing orientation of rigid bodies. Okay, robot gripper pose estimation can be done using Quaternion. Aircraft pose can be done by Quaternion, and anything actually. Game designer use it extensively because it is free from the problem which Euler representation has, known as gimbal lock. Okay, but the concept is very elegant and it's not new. You see, Sir William Hamilton, uh, 100 more than 150 years ago, actually invented this concept. Okay, and it is only now getting so much of popularity thanks to the programmer and game designer. It is everywhere actually in your mobile phone. The orientation is being calculated in the software. You see, it will be Quaternion, okay, because it has quite good um, and ease of programming and quite good representation, unambiguous representation technique. But fundamental of it is very simple, okay, and we are going to discuss now. Its basic is actually complex representation of complex number. Complex number in 2D. So any complex number in 2D, how do you represent? Is very well known to all of you. If not, then just see. Suppose I have axis, okay, and this is real axis, and this is imaginary axis. Okay, uh, normally represented by I equal to root over of -1. That is it. Okay, and say at any instant of time I have this is my vector. Okay, uh, it has rotated. It is placed at an angle theta, and say its coordinate is 3 2, and then say the same vector has rotated by an angle say 30 degree with respect to its earlier position, and then say somebody has asked me to figure out the uh, new coordinate at this position. So I can do very easily. How can I do that? You see, uh, 30-degree rotation has been given. So the quantity, the complex quantity. Okay, first of all, say this is my vector, say OR. So OR has two component equals to 3 plus 2i, right? So is a 3 2, these are all real number. If we, in generalized way, if we call a complex quantity q, w plus ix, then you see w, x, they all belong, they are real, okay, and it is 2D, and so OR belongs to two dimension, is a vector, right? So the representation of OR can be done in using complex quantity. This is called Argon diagram, by the way, okay. It's 2D, okay. Now as I told you, what will be xy, so just try to see uh, cos 30 plus I sin 30 is actually 30 degree, it has gone, right? So complex quantity corresponding to this position is this, multiplied by 3 plus 2i will give you a complex quantity this, which is, if you just calculate, it will be something like, don't worry about that, 1.59 plus 3.23 I. Okay, so just by multiplying this quantity, compressed quantity, with the given compressed quantity, you can generate xy. So x will be 1.59, y equal to 3.23. Okay, so how we got it? You can also get it like this. You see, this project, this is x from the fundamental, right? So this is actually your this is x. So OA, say OA, OA equals to x cos 30 degree plus theta, isn't it? Huh? And OB equals to y sine, sorry, OR sine 30 degree plus theta. Okay. Now you can consider OR as unit vector. Okay, so this could be unit. So OA will be cos theta plus cos 30 plus theta, and then sin 30 plus theta, and so the compressed quantity will be cos 30 plus theta plus I sin 30 plus theta. So this is equals to your OR vector. So earlier OR, this OR, this is in vector form, they are not changing, right? So even if we do not for the time being do not consider it as a unit vector, just a vector, okay, and you, if you just divide it by its magnitude, it will be unit vector. But I am considering OR my vector in the argon diagram, can be earlier represented by 3 plus I 2I, and now it can be represented after rotation cos by this. Okay, and since you know what is cos theta, theta is known in terms of 3 2, you will be able to land up here. What we have done without telling you, it's simply multiplication, right? So whatever angle it has rotated, you generated complex quantity, multiply it by this, and so very easily you see that kind of manipulation is very easy to know that what is the new. So this is complex quantity. As you know, it has several application in many places, okay, in engineering, especially electrical engineering, control engineering, right, robotics. Now Quaternion, what is Quaternion? Quaternion is actually an extension of this complex quantity in higher dimensional space. Okay, so let us try to understand what will be the what will be the complex quantity, complex number representation in 3D, by the way, in 3D, complex number. So here actually we had a complex axis I have a real axis. Now here I am trying to say creating another space where this is my complex axis, another complex axis J, and this is real axis. So this and this I am calling them orthogonal, okay, because real axis with this 90 degree, real axis with J 90 degree. So now I can create a space, three-dimensional space I J real axis. Okay, so this will be representation of, and what will be the complex quantity represented in this plane? say there is one real quantity plus xi plus yj, right? So in 3D, the complex quantity will look like this. Now say we are trying to extend it to 4D. That is what Hamiltonian did actually. Okay, in 4D, how to represent, how to represent a complex quantity. It will be same thing, you see. Now this is a real quantity, say real, this is I. Now I want, this is a real axis, j k, sorry, I am not giving this notation here because although they are vector, okay, they are not unit vectors, remember. So I, j, k, what they are all minus root over of minus 1, and they are actually complex axis they are representing. Okay, there's nothing complex, but it's mere representation, you see. And then we are landing to fourth dimension, and I can write any quantity there, xi plus yj plus zk. Huh? So this will be my representation of the complex quantity in four-dimensional space, which may not be the manipulation in that four-dimensional space may not be very intuitive because we are habituated up to 3 dimension. But there is a very interesting video I have referred here. You can see that intuitive, what you cannot get intuitively will be very clear if you see the videos. But we do not need that because we know mathematics, right? So any dimension, it's 4 dimension now, and this is nothing but Quaternion. This is Quaternion. Represented by Q, where X is, or actually W, X, Y, Z, they are all real. Okay, and this is in 4 dimension. Is it clear? So Quaternion is a creation of a 4 dimensional space having 3 mutually perpendicular complex axes, having one real axis which is also perpendicular mutually to all these axes. Now, uh, what advantage it has, we'll try to just tell you in the subsequent lecture, that using Quaternion, how, so it is again a vector, right? How rotation can be represented, and the difference between this vector and uh, vector having 3 cross 3 a rotation. So this is R, okay, say rotation matrix in the vector form, and this is vector. Uh, the unique property or the advantage it has, it is very friendly with the programmer. Okay, just you need to pass those values of x, y, z, and w, and accordingly you can generate your rotation, rigid body. You can describe rigid body motion, that means orientation, very easily, avoiding gimbal lock situation. Okay, so let us try to understand how this can be done in the next class. Thank you for your attention. Stay safe. Bye bye.